Welcome to the Explainer. Today, we're going to do something pretty cool. We're going to build an artificial brain, basically from the ground up. We'll start with just one single digital apprentice. Then we'll teach it how to think and watch it grow, piece by piece, into this powerful thing we call a neural network.
I mean, it's a huge question, right? But the answer is actually surprisingly elegant. What if a machine could learn just like we do? Well, that journey, it begins by looking at the most powerful computer we know of, our own brain.
Okay, so here's the game plan. We're going to start with that brainy inspiration, then meet our digital apprentice, the perceptron. We'll see how it joins a team to form a network, and then the really fun part, how we teach it to learn from its mistakes, get smarter, and finally, master its craft.
So let's get one thing straight. This isn't just about code and complicated math. Nope. At its heart, deep learning is really all about biology. It's an attempt to build an artificial mind inspired by that incredible network of neurons firing away inside our own heads.
And to understand how this whole thing works, this artificial brain, we've got to start small. Let's zoom way in, right down to its most fundamental part, a single, simple building block. You can think of it as our digital apprentice, who's about to get its very first lesson. All right, so it's time to meet this apprentice. In the world of AI, we call it a perceptron. And believe me, this simple little unit, this is where all the magic really starts.
So what is a perceptron? Well, you can just think of it as a single digital neuron. Now, it's not a genius by itself, not at all. But it is really good at one thing, weighing different bits of evidence to make a super simple decision. Basically, a yes or a no.
So how does it think? Well, it's a pretty straightforward three-step process. First, it looks at all the information coming in and weighs it, kind of deciding how important each piece is. Then, it just adds up all that weighted info. And finally, something called an activation function makes the final call. It fires off a yes or no signal based on that total. See? Simple, right?
Okay, so our apprentice is pretty good at its one simple job, but for the really complex problems, it's going to need a team. And this is where the real power of AI gets unleashed, when we connect thousands, sometimes even millions of these little guys together into a massive network.
So inside this network, information flows in a very specific way. It starts at what we call the input layer. Then it travels through one or more of these hidden layers. And those hidden layers, that's where all the real heavy lifting happens, the real thinking. And then finally, it all ends up at the output layer, which gives us our final answer.
Okay, so the network makes a prediction. It makes a guess. But how does it know if it was right or wrong? Honestly, this is probably the most important question in all of learning, whether you're a human or a machine. Because without feedback, you just can't get any better.
And that's where this next idea comes in. The only way the network can improve is by measuring its own mistakes. It needs some kind of signal that tells it exactly how wrong it was. In machine learning, we have a name for that feedback signal. We call it loss.
And this is absolutely the key to everything. The entire goal of training one of these networks is to just tweak all those internal connections over and over and over again with one single mission. Make that loss value as small as it can possibly be. It is all about minimizing mistakes.
But how do you actually measure wrongness? Turns out there are different ways to do it. You could use something called mean absolute error, or MAE. Think of that one like a pretty chill mentor. Every mistake is treated more or less the same. But then, you have mean squared error, or MSE, and that one. That's like a really strict teacher. It heavily penalizes the big mistakes. Which one you use really just depends on what you care about more. Avoiding a bunch of small errors, or avoiding one catastrophic one.
Okay, so now our network knows it's screwed up. It knows it made a mistake. But let's be real. Just knowing you're wrong isn't enough, is it? You have to know how to fix it. And this next step is the real key to how a network actually learns and gets smarter.
And this quote here, it really captures the big aha moment of machine learning. I want you to imagine that your error, your loss, is a giant hill. Now, something called the gradient, it tells you the direction of the steepest path up that hill. So if you want to get to the very bottom of the hill, which means minimizing your error, what do? You just take a small step in the exact opposite direction. Simple. You just walk downhill. And this whole process, this downhill walk, has a name. It's called gradient descent. And it is the absolute engine of learning for these networks. So think about the loop. The network starts with a random guess. It figures out the direction of most wrong.
It takes a tiny little step in the opposite direction, it updates all its internal weights based on that step, and then it does it all over again. And again, we're talking millions of times, until it finally finds the very bottom of the valley where its mistakes are as small as possible.
So our network is learning. This is great. But, of course, there's a catch. There's always a catch. We have to make sure it's learning the right things. Because just like any student, it can fall into one of two traps. It can either not study enough, or it can just memorize all the answers for the test without actually understanding any of the concepts.
And this is the classic balancing act in all of machine learning. You have underfitting, that's like our apprentice who just didn't study at all. The model is way too simple, and it completely misses the important patterns. Then you've got the opposite problem, overfitting. This is the apprentice who memorized the textbook word for word, but is completely useless when you give them a real-world problem they've never seen before. They can't generalize. They can't think for themselves.
So, what we're always aiming for is the ideal fit. This is that perfect sweet spot. It's where our model has learned the true general patterns from the data, but it's smart enough to have ignored all the random, irrelevant noise. And getting to this ideal fit, that's what allows it to make really smart predictions on brand new data it's never encountered before.
The good news is we have some really clever tricks to help guide our apprentice toward that sweet spot. There's something called regularization, which kind of gently nudges the model to not get too complex. Then there's a really cool one called dropout. It's like telling random neurons to take the day off during training. This forces the rest of the team to step up and become more robust. And then there's early stopping, which is basically like a wise teacher who knows exactly when to end the lesson, right at that perfect moment before the student stops learning and starts just memorizing.
So, after all that, what's the big picture? What's the main takeaway? It's this. A neural network learns by constantly, relentlessly adjusting its own internal wiring to close the gap between its guesses and what's actually true. It's a journey, right? It's all about trial, error, getting feedback, and making tiny, tiny adjustments. You know, a process that sounds an awful lot like how we learn, too.
And that kind of leaves you with a pretty fascinating question, doesn't it? I mean, if a machine's learning process mirrors our own so closely, what does that teach us about intelligence itself? Are we just incredibly complex biological neural networks slowly adjusting our own internal weights over a lifetime of trial and error? Something to think about. Thanks so much for joining me on The Explainer.